Okay, so good afternoon, everyone, and welcome to the International Perspective webinar series held by Go Study Global Education. This event is held on the 6th February 2026, and we are happy to welcome you as our audience for today. As for today's topic, we will talk about numerical simulation of heat transfer through multi-layered walls using ANSYS program. This topic is brought to you by an expert from National Polytechnical Institute of Cambodia. My name is Shafira, and I will be your master of ceremony for today's event. To encourage an engaging atmosphere, I encourage everyone to stay until the end of the session, and please don't forget to use the virtual background that our team has provided in the chat box. Without further ado, let us start the event. So I will start by doing the project introduction. So the International Perspectives webinar series is an event held by Go Study Global Education. This program is also jointly led by the CIMOTED, China Asian Technical Education Cooperation, and co-hosted by the Southeast Asian Sustainable Development Foundation, PASITA, and also Go Study. This program is expected to invite 1 to 2 school faculty members, and it aims to enhance and also enrich the growth of knowledge, also to broaden the horizons of learners in the Southeast Asian region. These online lectures will also help learners to acquire specialized knowledge through knowledge sharing and also cross-cultural understanding. So this is our speaker for today. We will have Mr. Kit Rayuth. Mr. Kit, are you here with us today?
Yeah, I'm here. Yes, Did you hear me,
Okay.
everyone?
Yes.
Yes,
Yes, we can hear you and we can also see your screen. Great. Thank you for being here, Mr. Kit. So I will
yes, thank you.
do the speaker introduction for Mr. Keith. He is a Deputy Dean of the Faculty of Mechanical Engineering at National Polytechnical Institute of Cambodia. He is also the head of the Lanchang Mekong Center, leading regional training of trainers programs and developing C1 to C3 technical certification SIMs. And he is also a PhD candidate in mechanical engineering and certified master trainer. His professional field includes mechanical engineering design, measurement and metrology, CAD or CAM, and also training of trainers. So we have him as our speaker for today. And without further ado, I will let Mr. Kit Rayuth to share his screen and start presenting his material to us for today. To Mr. Kit, I would like to kindly remind you that you have 70-minute times of presentation, and after that, we will have Q&A session. So everyone here are free to ask questions in the chat box, and I will read them to you. Okay, so for Mr. Keith, the time and screen are yours.
Thank you. Yeah, thank you so much, uh, Miss Sri Rida Andini. Yes. Thank you so much for your introduction. And so, first of all, I would like to, share my screen first. Yeah, here my screen. Everyone can see the screen now.
Yes, we can see them, sir. You can do it full screen. Okay.
Okay, yes. Wait a minute. Okay, my screen is not move.
It is on the screen now, sir.
Yeah, I share already, but it's not move. It's not move. Okay. Again. Okay, back to yes.
Yes, it is moving now.
Okay. Welcome to everyone. Yes, good evenings from Cambodia. Yes. Uh, good evening, Excellency, ladies and gentlemen. Today is my great honor and please sure to do online presentation with you all for the organized by Go Study for international webinar series, and thank you for the everyone to join with my presentation. So my presentation topic today is talk about numerical simulation of heat transfer through multi-layer wall so using ANSYS program. Yes, presented by me, Kit Ayut. Yes. So before I start, the topic, so let me to introduce myself. My name, Kit Ayut. I'm a lecturer of medical engineering in one institute named National Polytechnic Institute of Cambodia. We call NPIC, and my major is general mechanics. And for my education, nowadays I'm a PhD candidate at Institute of Technology in Cambodia. And I'm graduate master degree in South Korea, yes, in 2014. And I have experience on teaching, teaching for student, teaching for the master trainer training in company, yes, and also I'm also the coordinator of one of center in Cambodia and PSC, yes. And before I start do my the topic, let me to remind all of you about design philosophy. First, what is a design philosophy? Maybe everyone will be give the answer different. Yes, give the answer different. But for my preparing, I have only 4 elements. First one is talk about basic concept of machine design, and second one will be talk about the type of design. And the third one will be talk about the design basic on method, and the last one is talk about the factor to be considered in machine design. Let's move to the basic concept of machine design. Machine design will be we look on only 3 points. The first point we talk about decision making, and the second one we will be looking on market survey, and the third one will be mentioned about critical decision. This is the main point of the basic concept before we start to do the new product or new concept design. For the type of design, we have only 3. One is the adaptive design, second one development design, and the last one is a new design. Yes, the new concept or new idea to do the product to do the design. Yes, a good design. Yes, and for the the methodology, we look at rational design, empirical design, and industrial design. Yes, we have all the 3. And for the factor for and that consideration in machine design, we will be look at one is the what the device and the mechanism to be used, like material, load, size, shapes, space requirement, and weight. And we will look at also manufacturer, how to do, yes, and also how will be operate, and reliability and the safety also we look at. And the last one is the maintenance cost and heuristics also we look at. So I have only 6 part of the content. One is I will be mention about the introduction. Second one I will be mention only 3 the mode 3 of heat transfer. And the third one I will be look at the mathematics of the modeling of heat transfer for multi-layer of wall. And I will be talk about the case study 1 will be more detail about the 1D one-dimensional 3 composite wall for modeling heat transfer. And the case study 2 will be look at the 2-dimensional furnace simulation using ANSYS simulation. And I will be a summary, recap for you all. And the last part is a question and answer. So as everyone, some of you maybe you are familiar, or some of you maybe know. Yes, because this section, webinar section is very good for you all. So we will be look at about how we do and discuss some the concept of the heat transfer, and heat transfer have the three mode like I mentioned at the beginning. The first one will be look at the heat conduction, heat convection, and radiation for the three mode. And for my case study, I will be look at only heat conduction because we be apply the temperature for inside and outside our wall, and we will be give some formula using mathematics, and we be use NZ program like I mentioned at the beginning of my presentation. So for the and this kind, I will be use NZ, and I will be select the steady state solution for heat conduction of 1D and 2D dimensional cases. And like I a little bit mentioned about the case study 1, case study 2, I will be apply a program for validate in the case study, yes, in case study 1 and case study 2. So the using ANSYS, so I'm also thank you for the ANSYS software program I using to simulation for the condition is steady state, and I will be show you guys in the next slide. And it's for to use in simulation, we have to get information to data setup for the ANSYS program, like we will be to choose the material. Material is important for ANSYS, or for the to make the wall of the layer on the wall will be cut out the temperature. Don't be we maybe, as well, temperature will be moved from the high temperature to the low temperature, so we have to select the insulation of wall better and better, and make the temperature will be slow down to transfer. And I will be give you some a little bit about the unit and dimension of the as you guys know well about the unit, like a length will be unit of the feet, or is a American standard, and for the metric will be choose the mètre or millimeter. Depend on the situation. And mass, pound, and Newton or kilogram, yes. And time will be go to the second or minute or hour, depend, yes. Temperature will be go to the degree Fahrenheit or Celsius, yes, Celsius. And for like I mentioned, and some of data like we look at like electrical current, like thermodynamic temperature, yeah, plane angle and solid angle, yes. And I also, yeah, sorry, yes. And we have the another like force, maybe Newton, pressure, stress, energy, power, yeah, something like that. And also I have some multi prefix of like pico, nano, micro, milli, centi, yes, hecto, kilo, mega, giga, and tetra. And before we start to calculate, we have to understand or clear about the unit. Yeah, unit is important. And like I mentioned at the beginning, yes, for the heat will be moved to the from high to the low, so we have to select the thermal conductivity, the material for thermal conductivity. We will be look at the like the metal and non-metal, yes, liquid and gases. So I put the slide on the slide, the table, yes, to mention the material like silver, how the thermal conductivity. So the silver will be the property is 418 kilowatt per mass multiplied by Kelvin, yes. Also copper, yes, aluminium, zinc, iron, lead, and non-metal like quartz, corundum, marble, ice, yes, pyrite, glass, like the liquid, like the mercury, water. So I'm not read at all. So I will be pass through to another material like diamond, copper, steel. Like one of the I use is steel, also glass, also some material like glass wool or bricks also used. And here's some of the graph for the small conductivity. Yes, small conductivity. The unit is watt per mass multiplied by Kelvin or Celsius. Yes, depend on. So like the stainless steel, brass, aluminum, copper. You can see the slide. Yes. And yes, for the next one is I mentioned about the mode of the heat transfer. So like as you guys know, yes, the the three mode of heat transfer mean are like the conduction, convection, radiation. So the heat flow depend on the temperature different. And you see the person I'm take from the books. So you guys see the temperature. The first picture one talk about temperature of the person will be 198.6 Fahrenheit, and the outside is 75 Fahrenheit. So the heat of the body person will be transfer to the outside. And also that's the second one also, the body of the person will be, and the outside is 50 Fahrenheit Celsius, Fahrenheit. So the body temperature will be, transferred to the outside. But for the third picture, you see the outside temperature is 100 Fahrenheit. So will be transferred from the hot temperature to the low temperature of the body of person. Yes, it's the heat transfer. And I will be give you some heat conduction is the heat transfer of heat through material by the direct contact of matter. For example, you see the person how the heater will be go through the material, for example, like steel material, and you heat it up, so the person handle will be feel hot. And if you put the insulation, when you hand over, so it's not direct, go through the right of a hand because of the insulation. Yes. And I give you some, formulation, basics formulation, like, pH, mean heat flow, unit is watt, and K is thermal conductivity. Like I mentioned, the unit is a watt per mat, multiplied by Kelvin or Celsius. And A mean area of cross-sectional is, unit is a mat square. And T1, T2 is a temperature different from hot to cold, yes. And the L is you mean length, yes, length. And I go to the next slide is mentioned about, the heat convection. What is heat convection? Heat convection is the heat transfer also, but the motion of the liquid and gases. Mean the heat maybe, heat will be, by free convection or by forced convection. For example, you see the person, it's not direct get the hot temperature from the lights, because of the we feel the hot because of the convection by the, like I mentioned, the free or force. It will force mean you use another tool like a fan or air, yes, go through our hand, so we feel like move by the hot. Like for example, you see the water tube in the pump, by pump, yes. And I give you some information, some about the formula is pH about heat convection, mean heat flow, pH, and different from the previous of the conduction. Is we not mentioned about the small conductivity, but we mentioned about the heat coefficient, yes. Coefficient. The unit is a watt per mass square multiplied by degree Celsius. Yes. A is mean area contact liquid fluid of unit is a mass square, and the temperature from hot to cold, T1, T2. Yes. Yes. It's that's all for the heat convection. And the last one is heat radiation. Heat radiation. What is a heat radiation? Heat radiation means heat transfer by the electromagnetic wave by waves. So like in we cannot see the thermal radiation because it will occur by the infrared wavelengths, invisible body eye, yes, human eyes, sorry. Object include different color from the temperature. You see the sun, yes, sunlight, and will be give the heat or temperature to the earth. So I mentioned about some color, like everyone maybe well about the physics. They mentioned about the color, which color are get high temperature. Maybe you guys know, yes. For the red color, the temperature of well of the temperature is lower than another color, like blue, or like green, yes. That color is because of the valve, yes, valve. And I give you some the equation. Q mean the thermal radiation, yes, and emiss epsilon mean emissivity, absorb, relative to absorb, and the Boltzmann constant. We give some data is about 5.67, yes, multiplied by 10 minus 8 watt per meter square, multiplied by case yes, for 4, yes. And S mean cross sectional, like I mentioned, and this one is the temperature of the surface and surrounding, yes. Yes, for the three mode of the heat transfer is at the end, yes. And I go to the numerical modeling of heat transfer multi-layer of the ball, yes, of the ball. So this picture I select 3 ball, mean layer 1, 2, 3, and the temperature of TC goes to the temperature of F, from TC to F, because of the TF is low temperature, and will be the composite of wall. This wall will be be we know well about the thermal conductivity and the condition of the heat. So we also know about the some coefficient of friction, yes. And this one, like I mentioned, yes, we also look at the heat conduction. Yes, I'm not read the slide, but I will be give you some the equation we use is a Fourier law, mean the Q equal minus K multiplied by A mean cross sectional area, multiplied by derivative of the temperature divided by dH. Yes, so we change the temperature from 1 to 2. Yes, so we build the sum of the equation, and like I mentioned, the Q mean heat transfer heat conduction of the unit is watt or kilowatt, depend on, yes, and K mean thermal conductivity. Yes, the unit is watt or watt per mass multiplied by Kelvin or Celsius. For the cross-sectional area, mean the unit is a meter square or millimeter square, and L is length of the insulation material. Unit is meter or millimeter. And for the formulation, we use the heat flux through the layer of the ball. So heat flux means the Q dot. So is depend on the heat transfer of heat conduction divided by the cross sectional area A. So the formula will be go to the last is a K T1 minus T2 over L. So the unit of the heat flux is watt per meter square, yes, square meter. And here resistance of the heat, so we we depend on the layer over by the small conductivity and multiply the cross-sectional area. Yes, it depends. Yes, and so the formula of the heat flux will be this one. Yeah, and not read it. And so we is a substitute after this formulation, and this one you can see on the slide. Yes, T inside minus T outside, and divide by resistance of the heat in each layer. Yes, from inside to outside, and from the the each wall to from the layer 1 to layer 3. Yes, and this one is a formula. Yes, the last one we divide it. Yes, and so, and also we can find each case of the the heat flux in each layer. Like layer 1 will be the formula will be Q dot is K multiplied by A, and the T1 minus T2, and depend on the layer, the thickness of layer. Yes, and second layer as well, and the third layer as well. Yes. So like mentioned, the heat flux unit is what? Watt per mass square meter. Yes, sorry, mass square meter. And for the temperature difference, at the beginning, at the previous, we mentioned about the heat transfer, heat flux, and this one we mentioned about the temperature difference cross. Yes, cross the layer. Yes, cross the layer. So the result from this equation will be T1 minus T2. So will be equal by of the heat flux multiplied by layer of the each wall. Yes, layer of each wall, and divide by small conductivity of each you know material. Yes, different of material. So the next slide maybe you guys will see the what is the small conductivity of the material different. Yes, and multiply by A, it means cross sectional. Yes, and also T2 if you want to find the T2 or T3. So T2 minus T3 and equal by heat flux and layer by layer. This one is stainless steel, and in this case for the my case study will be the next line. So I will choose the stainless steel, the layer 1. The second layer I will be choose the ceramic bridge, mean the classroom, and the last inside one the I will be choose the fiber bridge. Yeah, bridge. So you guys will be see. Yes, on the next slide. For the case one, one-dimensional 3 composite of wall of the modeling heat transfer. Yes, and the case the star case study 1, I will choose the top part of the furnace class. I choose the 300 degrees Celsius for heat. Yes, it higher one, and the low temperature I will be choose the yes 50, yes, 50 degrees Celsius, like you see the slide. Yes, so like I mentioned, the temperature of heat will be moved from the hot, so 300 degrees Celsius will be move temperature to the surface of the wall. As you see, yes, you guys, yeah. The first layer, like I mentioned, is fabric and insulation we use because of we cut down, yeah, we cut down the temperature to the outside to the surface, so of the steel. Yes, so BBB C in this. So I the short cut of word I will be choose the LFB mean the layer, thickness of layer of the fabric, and LCB mean the layer of insulation, and the LSS mean the layer of stainless steel. I mean, this case I will choose the stainless steel to make the the furnace class. And like I mentioned, for this slide table, I will be the layer of the material, like I mentioned, stainless steel 304 the thickness, I will choose 2 millimeter. And small conductivity, it's depend on the condition of temperature. So I choose 21.5, yes, yeah, watt per square meter multiplied square meter, watt per mat multiplied by Kelvin or Celsius. And the another one is a ceramic blanket, I mean glass wool. So the thickness is 25 millimeter and small conductivity is 0.17. Yes, and for fabrics will be thicker than another. Yes, it's 65 and the small conductivity is 1.95. So go to the mathematics. So for calculate heat transfer through the multi-layer, so Q equal by K multiplied by temperature difference delta T. So we have to find the K first. Overall heat transfer coefficient K. So like I mentioned, is the formula is 1 over by the different of the layer and the different of the coefficient of condition. Like the H1 I will choose 100 and H0 I will choose 25 is a condition. Yes, and so the each layer like mentioned on the table, you see Celsius zero, the thickness is 2, so I to better to calculate, so convert it to math. So it will be 2 multiplied by 10 minus 3, so it will be 0.02. Yes, divide by ks. You see the thermal conductivity on the table, everyone, you see is 21.5, right? 21.5. So also the second layer is 25 millimeter, so convert it to math, so maybe to 0.025 millimeter divided by 0.17 on the you see the slide. Yes, thermal conductivity. So also the another case is fabric is 0.065 divided by 1.95. So the total number is around 4.30. Yeah, 867. Yes, you see. Yes, and watt math Kelvin. Yes. So as I mentioned, so we go to substitute to the formula. So because of the temperature hot is what? It's 300, right? 300. So 300 and the surface temperature is 50. Yes. So we multiply. I take only from the calculate is 4.3387. So if you calculate it's long, yes. Yes, so the total is calculation is the 10,084.65 watt per square meter. Yes, it's the answer. Yes, so we go to the next case is we find the temperature, the difference of the T2. T1 we know it, but the T2, how the T2? T1 is 300, but the T2 is what? T2, like I mentioned the previous slide, you see, you guys, yes, T1 minus T2 equal Q, yes, multi the layer of the fabrics divided by thermal conductivity, multiply cross-sectional area, yes. So we substitute the number, the amount of the each one of the calculation. So T1 is 300 and Q we calculate on Abu, yes, 10,084.65. So the multiply 0.065 divided by 4.3386. So the answer is 283.75 degrees Celsius. So yes, you see the temperature is slow down, slow down transfer. And we find another temperature is T3. What is T3? T3 is a function of T2. T3 is equal by T2 minus Q multiplied by LCB, semi brick, I mean, yes. and divide by thermal conductivity multiply by cross-sectional area. So it we substitute the amount of the number. So the answer is 227.5 degrees Celsius. So that's heat transfer, heat will be transfer is low and low, yes. And by the case, so we find T1 we know, T2 we know, with T3 we calculate it, yes. So now we you know, we use another program to validate it. So the case study, yeah, case study one. So we use the ANSYS software simulation. So for this program, you guys should be installed in for the student version, and for my case I install it for ANSYS 2021. It's depend on you, yes, and release first one, and you can choose. And for to start to do the ANSYS program, because we don't have enough time, so you guys can see can find the example through the YouTube. Yes, go to YouTube and you can see how to use the ANSYS software. So in my case, let me introduce some of this start of the using ANSYS. So the better you should be, have the program ANSYS first, and then second one you study what is the project will be started. So in my case, I use ANSYS and then I design modeling. I mean modeling. You see the layer of each wall. You see layer of each wall. So I have three. The first one, what is that? Is outside is stainless steel. Second one is glass wool, and the third one inside is bricks. So we have to do 1D or 2D first, and then you go, and when you have the file of modeling, you can draw on the ANSYS software as well. You can draw it, or you can use another software like SolidWorks, like Fusion 360, yes, or like Solid Edge, yeah, like CATIA, and then if you want to choose another software to modeling, and then you have to check on if you want to to use ANSYS. So you have to look at the file cell to import it in ANSYS software. So ANSYS software we support with another software as well to modeling. And then after you do a modeling, you have to set up the data of material engineering. Material engineering means each layer you choose it, like steel, like many of the material, like steel, like ceramic, like glass wool, like another material, yes, like mentioned in the slide. So in my case, I'm modeling first, and then I choose the material, and then I go to to set up because my study case is is the heat transfer. So I choose the heat for the thermal steady state, the condition, and then I set up the data like the hot temperature to the low temperature. So based on that, when I set up, you see on the slide, the low temperature is 50 degrees Celsius minimum, and the maximum is 300. So if you want to check the layer of temperature for compare to the calculation, like in the previous slide, so I use the prompt on the software, and you can see the hot temperature is 281, right? 281.21 degrees Celsius, and the second layer is 29, sorry, degrees Celsius, and near the surface is 132.31 degrees Celsius. So it means the temperature is low, yes, low from the hot to the surface, yes. And this graph is mentioned about the layer function of temperature. So the temperature will be down, will be transfer by the heat. Yeah, heat of the heat depend on the thickness of the material. Yes. And I have the video. Yes, video. You can see how it's work. Yes, you can see. Wait a minute. Yes, this one is and this simulation. Yes. Okay, you can see. Yeah. One more time. So heat will be moved from the hot to the low temperature. Yes. Okay. Yes. Let me go to another slide. And this one I will be because I use NC software, so I want to check the heat profile, heat pass it, how it's move. You see, go from number one to the number two. Heat will be transfer. Yes. Also, I have the video. Wait a minute. What? Yes. One more time. Yes. Yes. Okay. And the comparison of, the first one we look at the heat flush or thermal flush, and the second one we will look at the temperature between the fabric to the insulation. The third one we will look at the temperature between insulation to the surface of the wall, mean the stainless steel. So when we check it to verify, to compare it. First one we use the mathematical numerical, yes, numerical model, numerical model. The number of the is 1084.65. For the software, and this software is 1397. Yeah, the number. So it's quite big. Yeah, quite big different from calculation to the software. For the temperature of each layer from ceramic brick to the insulation, you see the calculation is 283.75, but for the software is 281. Yeah, the number. So it's like, yeah, similar. For the last part is temperature between insulation to the to the surface. For the calculation is 277.5. For using the ANSYS software, the software is 257. So mean for simulation is this the number is quite lower than the calculation. Yes. And for the case study two, yeah, for the case two, I mean case two, not case one, case two mean I maybe choose the temperature is higher, yes. One inside is 300 degrees Celsius, and the surface, that one I choose the 50 or so, yes. And for the material, the same, yes. Inside ceramic bricks, insulation, and the surface steel, yes, steel, stainless steel. So also we calculate by overall heat transfer coefficient K. So K, the number calculation, like mentioned in the previous, it is slightly similar. Yeah, similar. Yes, similar for the K. So for 4.338. Yes. So we calculate the heat flush by mathematics. So 4.3386 multiplied by 600 minus 50. So the number is, the calculation is 2386.23 watt per square meter. So you guys will remember it. So we will compare it to the next slide. Yes, we compare with the software. Also, we calculate by the mathematics. We find the T2, but T2 is a function of T1. T1 minus T2 equal Q, yes, multiplied by the thickness layer of the fabric divided by thermal conductivity multiplied by cross-sectional area A. So if you calculate it, the the number is T2 is 564.25 degrees Celsius. It's T2. How about T3? It's like similar. Yes, T3 equal T2 minus Q multiplied by thickness layer of the ceramic brick. Ceramic brick, I mean glass wool, divided by the mole conductivity multiplied by cross-sectional. So the calculation number is 350.48 degrees Celsius. It's T3. And the same, yes, like I mentioned, yes, slide slide similar to the case one, but case two, we we choose the temperature of 300, but the case one is 300, right? Yes. So if you check it on the software by using software and this software, so the surface is 50 degrees Celsius minimum and the maximum is 600 maximum, yes, temperature. So we can check it. I choose a prompt to check the property of the each layer. So the first layer around temperature is 592.48 degrees Celsius, and for the second one is 558 or 59. Yes, like yes, yeah, the number is, and the layer is 509.79, and another layer is 185. So the temperature will be down, yes, some temperature down because of heat transfer. And also of the graphs mentioned about the temperature is depend on the layer, the thickness layer of the material, yes. And I have the video, so you guys can see it. Video, yes. Wait a minute. Here. One more time. Yeah, heat will be transfer. Yes, transfer. And also I mentioned about the heat profile. Heat pass go to the surface, and in the number one go to the number two. You see here? Yes. And I also have the video. Wait a minute. Okay. Yes. Once again. Yeah. Yeah. And this comparison, yes, the table comparison of the using numerical model and I mean mathematics with the software. So heat flush, thermal flush, thermal flush, and temperature between the fiber brick to the insulation, and the temperature between insulation to the steel, such as stainless steel, yes. For comparison is mathematical calculation is around the heat flux, you mean the 2386.23 for them, and this is around 3073, yeah. For the temperature between the fabric to the insulation 364, yes, 564 for the software is 558, yes, a slight yes, similar, yeah. And for the temperature between insulation to the stainless steel for the calculation is 550, yes. And for the ANSI software, using ANSI software is 509, yes, 509. So yes, slightly different, yes, slightly different. And I'm just finished for the case study one, and I go to the case study two. Case study two, I will mention about the two-dimensional furnace simulation using ANSI software, yes. For this one, I will be choose the temperature inside 300 and the surface is 50 to to check it. The heat will be transferred, yes, from the hot to the cold, like I mentioned on the slide at the beginning. And so the temperature I also mentioned about it depend on the thickness of layer and also depend on the material, yes, material of insulation. So if the insulation have the thermal conductivity of the material is lower and very good, and the heat will be cannot be go through to the outside hot, yes, so will be cut out by the insulation. And also this one I have the video. You see temperature, yes, once again temperature move, yes, transfer from the hot to the low temperature, from inside to the outside, yes, yeah. And so this one I set up for checking the temperature profile from the number 1 to the number 2, yes. So you can see on my video, my simulation video, yes, you see, yeah, heat from the hot to the low, like I mentioned, yes. And another one is to find the heat flux, total heat flux, how it's work. So if you see on my simulation, heat flux, the temperature will be, yeah, once again, yeah, at the edge side, yes, because of my geometry it will be a square of the 2D, yes, square 2D. So also I will be choose the heat flux profile of the heat will be from the hot to the cold. So the number, yes, number of the value, I mean the value of the heat flux number will goes, you can check it on the slide, my slide, yes. And the heat flux is also depend on the layer aspect, the thickness layer of the material, yes. And you check it. Also, I have the video as well here, yes. Yes, like similar, yeah? Yes. Once again, yes. From hot to the low temperature, surface, I mean surface. And this I summarize of the data, the value from the simulation. Like first one is a heat flux. Second one, the temperature between fabrics to insulation. I mean to glass wool. The number, the value, you can check it on the slide, yes. And the third one is temperature between insulation to the stainless steel, I mean surface. So the heat flux number is around 5,425.9, yes. And for the temperature between fabrics to insulation, around 222.22. And the temperature between insulation to the surface of the steel, stainless steel, I mean, 77.70, yes, 77.8, yeah. And for the condition, I mean the case 2, I will apply the temperature is 600. The first one is 300, but the second one is 600. So you can see on my video. Yes, once again. Okay, so like I mentioned, again and again, for the heat will be transferred from the hot to the low temperature, yes. And this one we will see easy to see the temperature profile or temperature path, yes. you can see on the my video. I also prepare it. Yes. Once again. Yes. 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 And so the temperature will be also transfer depend on the layer of the insulation, the layer of the material. Yes. And this one is I mentioned about the total heat flux. Total heat flux. So you guys can see the video I took from the software. Yes, software once again. Yes, yes. And also we can see through the heat flux profile. Yes. So the heat will be moved from the hot inside to the surface of wall. Once again. Yeah, yeah. So too easy to understand. So I summarize through the table like the heat flux. The value is 11,000. Yes, 900. 37, and the temperature between the fabric to insulation is 538.89 for temperature between insulation to the stainless steel 304 is 172.22. Yes. For this end of the heat transfer, and we apply my mathematics and ANSYS software. So for my summary, yes, we have to understand more deeply about the three mode of heat transfer, like I mentioned on the slide, mean the heat conduct, heat convection and radiation, and like I use the case study one mentioned about one dimensional of the heat transfer of the three wall layer by different material, and also 2D dimensional of the furnace layer. And we also have to use the mathematical equation of heat transfer for compare with the ANSYS software to verify how is the number are quite the big different or small different. Yes. And I have also summarized through the table in the table 1.5 summary. Yes, you see here. Yes, I took from textbook. At the end, I show you the reference I take from. So the mode, like I mentioned, mean heat conduction, convection, radiation. So this one is a mechanism of the heat and rate of the equation, and the number of equation and the unit of equation. So, and also here is reference. The reference I took from a fundamental or heat and mass transfer, and software you guys can go to the ANSYS. Yes, ANSYS.com, and you can free download for student version, and also we can learn by this website. And yes, very good, you can go it there. Yes, this one is the end of my presentation, and if you have any question, and please and feel free. Yes, thank you. Yes, in my contact, everyone can email me. Yes, my email and phone number, Telegram. I also use Telegram and WeChat. And the right hand side, you see is a picture of the capital city in Cambodia, Phnom Penh. Yeah, so you guys can sometime you can visit us. Yes, welcome you. Yeah. Thank you. Yes, thank you. It's my end of my presentation. And if you have some questions, so I'm um give you. Yes, please.
Okay, thank you very much, Mr. Kit, for the very clear and interesting presentation. Your presentation reminds us how important heat transfer analysis is in designing furnace walls, especially in choosing materials and also layer arrangement. Thank you once again for sharing your rich insights, especially when you add important details such as mathematical equations in your study cases. It feels like we're not only doing webinar, but we're also doing a lecture with you. That is very interesting. Okay, everyone, we will start doing the Q&A session. Please wait for me as I share my screen.
Okay, okay, yes. Mm.
Okay, so we will now start doing the Q&A session as I have seen a few questions here. So maybe we can start from a question from David. It's a very long question, but it's okay. From practical simulation experience, thermal bridging cannot be treated through average or effective thermal properties. It has to be modeled explicitly as real high conductivity solid path in 2D or 3D because heat always finds and short circuits through studs, fasteners, and frames. Otherwise, heat losses and consistently underestimated. In ANSYS multi-layer wall simulation, how do you implement these thermal bridges realistically in the geometry and meshing? And what typical errors have you observed when simplified or homogenized approaches are used instead? Thank you, Professor. Maybe Mr. Kit can answer this question from David.
Okay, thank you so much, Mr. David, for your long question, and also thank you. Yes, very good, very good question because because of the time is limited, so I'm not go more detail about the software simulation, but I can give you some. If we have chance next time, I will be show you how to set up the data, set up the on the parameters through the software. For your mention, right, for the heat set up through the parameter like I mentioned, thermal conductivity. If we don't know the value of the thermal conductivity, and to clarify with the software, we cannot simulation it 1D, 2D, or 3D. But 3D we need take a long time, like you mentioned about the mesh. For my condition, I take the value of mesh is the 2 or 3 or 5. Yes, if you put the number of mesh is small, it's it quite take a long time for simulation. As you know well about the software of using and this, we have to good PC, good, I mean, high speed of PC like RAM and CPU. So if you don't have the enough space for this to simulation, result is not appear. Go to the math, and also another parameter like I mentioned, for the modeling is more important. How is the geometry of the modeling, like the length or the thickness or the size, something like that. So we have to understand how the modeling will be goes through. If you have more information about the modeling of the geometry, mean that you can go to set up the data of the material like I mentioned in my slide, and we set up the property of the thermal conductivity, the density, the something like that. So Yes, like I mentioned, yeah, David can be go through that, yeah, go through to the simulation. Yes, thank you for my. I don't know where is my answer is catch you or not. I don't know. Yes.
Okay, thank you, Mr. Kit, for
Yeah.
answering the first question. For
Yes.
David, I hope answer from Mr. Kit can satisfy your curiosity about a few
Yeah, I hope so.
questions.
Yeah, I hope so.
Okay, I think we can do question from Andrew. Is there a rule of thumb on acceptable percentage difference between numerical simulation and ANSYS software simulation? From Mr. Kit, I invite you to answer.
Yes. From uh, which like I in my case study, I choose the book from the heat and mass heat transfer. So um sorry the math will be help us will help us to calculate by heat transfer. Yes, by heat transfer. Yes, by heat transfer through three mode of heat transfer like heat conduction, heat convection, radiation. And if we compare to validate of the with ANSYS, if we have we have enough the data set up between we use the numerical and software. It's quite similar. It's quite similar for that result. It's quite yes. The error around 5 or 10%. Yeah, 5 or 10% based on my experience. So we can use to validate for that. And the most important point, we can validate with experiment to compare with three. But for my case study, because our, my preparing session is short, so I'm not enough time to prepare with experiment. Is one of the to validate of the compare with the numerical and software and experiment. If we have three those of the three, we can validate each which one is a better way for that value. Yes, thank you.
Okay, thank you once again, Mr. Kit, for answering Andrew's question. For Andrew, I hope it answered your curiosity as well. I think we can move on to the third question. This is a question from Chava. First of all,
Sure.
thank you so much for your great presentation, sir. I have a question. In real industrial settings, what factors could reduce the accuracy of heat transfer simulations and why? Thank you in advance, sir.
Thank you. Yes, Iva. Yes, thank you so much for your pay attention with my presentation. Yes, maybe my presentation maybe a little bit fast. I don't know well, but maybe because we have the time limit. So for the heat transfer is a very very good in the case study like I mentioned for example in the furnace, those kind different furnace like the glass furnace or the kiln for the heat transfer between the heat sink to the electrical board, like the PC on the PC case, you see, also have the heat transfer also. Yes, and also environment like I mentioned in my slide, you see the sunshine also heat, so heat will be transfer from the heart to the our body, our humans, our us to the us. So the most of the those things heat transfer very very broad topic about how to deal with it. But in a chaos study, we can apply heat transfer for the case like I mentioned for the furnace, for the electrical, for the electric mechanical, especially in mechanical like aircon. Yes, like nowadays we mentioned about low carbon building also apply heat also. If the building have the temperature is hot like our country, the most of the weather is hot and hot, so that's why the will be temperature will be moved from outside to inside. So that's why we have to use air conditioning, HVAC, I mean HVAC. So to do with in that protect, we have to study about the insulation of the building. Also, we apply heat transfer as well. So it's my short question. I don't know if my answer is correct or not. So yes, thank you. Thank you.
Yes, thank you, Mr. Kit. And for
Yes.
Chava, hopefully answers from Mr. Kit can answer your previous question. Yes,
Yeah, yeah.
and we have went through three questions. Thank you everyone for asking and pay attention. We can move on to the first question. This is from Rifda. Dear Mr. Kit, thank you for your insightful presentation. I'm
Mhm.
curious about how could this type of simulation help improve energy efficiency in industrial furnaces? For Mr. Kit, you can answer Rifda's question.
Yes, thank you. Thank you so much. Um, again, so for the software is not it cannot to give us more the end of the answer, but the like the NC software help us to understand the like the graph, like the the temperature for based on my case study. The most important thing of parameter is temperature and heat flux. So for validate efficiency, if you want to get efficiency, we can compare with another software like we can use the like the Excel, or you can use another software like MATLAB or another software to to compare efficiency how it's work. So like I answered in the previous question, if you want to know the the error of each value, you should be do three things. One is the what is the mathematic, I mean numerical analysis if use of software, and the third one is the experiment. If you want to get the efficiency which of the heat will be good or not, we can do another thing like experiment. Yes, and yes, that's all for my answer. Yes.
Okay, thank you, Mr. Kit, for breaking the
Yes.
answers into three steps that we must look forward to. Okay, let's look into the chat box again. Oh, Chava asked again. Thank you for the answer, sir, but I have follow-up questions. I'm kind of curious, why do you think the results from the numerical calculations and the ANSYS simulation are different, even though they model the same wall system?
Ah, yeah, yes. Thank you, thank you. Yes, Java. Yes. You know, it's quite if we check it on the mathematics, I mean the heat transfer through the mathematics and the result from the ANSYS, it's some of the temperature are quite similar. Why we choose those two things to compare it? Because if you only use the mathematics, use the heat transfer of the mode of three things in the mathematics, is not enough to get the result. If you want to know more the value, more the result is a good, is a correct or not, we have to compare with another like the software, also like software and the experiment, like I mentioned again and again. Yes. Yes, in my short answer. Yes, thank you.
Okay, thank you very much,
Yeah,
Mr.
yes.
Keith, for answering another Chava's question.
Mm-hmm. Mm-hmm. Sure,
Okay,
yes.
I will scroll through if there are any questions that I may have missed. And for anyone who have yet to ask your question, please feel free to ask.
Mm-hmm. Okay, okay, I can check it.
Okay, maybe we will wait a minute for the others who have yet to ask questions, or else maybe we can wrap up this event. So everyone, please feel free to write your questions in the chat box.
Yes.
Oh, okay. I think I see a question from Rifda. I'm sorry if I have missed that one. So I have a question about how important is material selection compared to wall thickness in controlling heat transfer, especially in region like Southeast Asia. Yeah, this is a very interesting question. Maybe Mr. Kit can answer this one.
Okay, again, please. I cannot hear you well.
I have a question about how
Mhm.
important is material selection compared to
Mhm.
wall thickness in controlling heat transfer, especially in region like Southeast Asia, sir.
Okay. For selecting material is like I mentioned is a very important. Based on my case study, I build on my project. I build the furnace on especially on glass. If we choose the wrong, I mean another way for the another way to I mean the wrong material to build up the my project to build up the furnace is the result is not get well. It's not get well. So to go that thing, we have to do the literature review more detail about the property of the material. So before we select it, and we read more uh, article, more paper, and they mention the different material. And after that, we have the synthesis to have the idea how we can choose a good material, for example, like insulation, for use it to build up in the project. Based on my case study, I choose the um, glass wool specialist on the the furnace. So in that case, if we don't have enough data on the material, the calculation and the simulation will be failed. Yes, you get my point. Yes, thanks.
Yes, okay. Thank you, Mr. Kit.
Got this.
With that, I hope that
Mm.
answer your questions that there are also other aspects that we must look forward to in order for everything to go smoothly.
Mhm.
Okay, and maybe we have another question from Ridwan Ibrahim. What is the file extension to save our model in SolidWorks to be able to simulate in ANSYS?
Okay. Yes, the file for thank you, Mr. I can see him. Yes,
Mr.
Mr.
Ridwan.
Ridwan, yeah, Ridwan Abraham. Yes, for the file, we have a lot of file saving to to communicate with the SolidWorks to the entities. So for example, one is the you should sell it to file .igs .igs is good to import file modeling, and you can use this file to your own purpose. Like for example, you will use the thermal steady state condition, or you can use for the statistic structure. You can use it. And for another, yes, because ANSYS have the support many software, yes, of the like the SolidWorks or SolidEdge or another. But the most one I based on my experience, I recommend you to use IGS, yeah, IGS, not IGS file. It's better, yes.
Okay, thank you very much, Mr. Kit, for answering Ridwan's question. Ridwan, I hope
Yeah.
that answer is informative and helpful for you. So we
Mhm.
have another question from Paul Andre. He said that, good day and thank you for your informative webinar. I learned a lot about the three modes of heat transfer and how mathematical equation and ANSYS software are used to analyze furnace wall systems. My question is, why is numerical modeling, such as ANSYS, is needed when we already have mathematical equations for heat transfer? Thank you very much.
Yes, thank you. Yes, thank you. Thank you, Paul Adrit Aspiritu. Sorry, I'm not well right. Your correct and read your name. Yes. You asked me why it's a numerical yes model and this need when it's we really have a math equation for heat transfer like I mentioned in the previous question. If you have looked at on the one of the mathematic or numerical model one way we cannot compare the result which of the the model of the using ANSYS will be do correct or not, or we can validate in each two way, or if you have background on mathematics well, so it's quite good, yes. But we also to compare it how is it go to the right way or not, or we can check it error for error we can have to another way to compare it, yes. Like yes, like mentioned, yeah, the quite the same question, yeah, to another previous, yeah.
Okay, thank you very much, Mr. Kit, for your answer to Paul's question. Once again, Paul, thank you very much for the question, and I hope Mr. Kit's answer can satisfy your curiosity. Okay,
Yes.
everyone, I think this Q&A session will be concluded. Thank you, everyone who have participated in asking questions to Mr. Kit's wonderful material for today. Okay, now we will do the next session, which is the group photo. But before we do the
Yes.
group photo, I would like to inform everyone that we have an Instagram account used to share our events, programs, and also activities. The Instagram is at username pasita.education, as my team have shared in the chat box. So please don't forget to follow our Instagram to stay updated on our upcoming events, programs, and also activities. Okay, and now we will conduct the group photo. So please everyone to open up your camera and also use the virtual background that our teammates have provided in the chat box. I will wait 30 seconds. I hope that is enough for everyone to prepare.
Okay, thank you. Yes. Okay, good, quite good, yes.
Okay, everyone, please don't forget to use the virtual background. It is already being sent on the chat box by our colleague.
Okay, yes.
Okay, I see that everyone has turned their cameras. Okay, we will start to do group photos now. Okay, on the countdown of 1, 2, 3, smile. Once again, 1, 2, 3, smile. Okay, thank you everyone for participating in the group photo. Now we will close the event by
Yes,
sharing
thank
the
you.
attendance link by our college. And once again, for Mr. Kit Rayus, thank you very much for participating in
Thank
our
you.
event as the
Yes, thank you so
speaker.
much. Yeah,
Yes,
thank you so much.
yes, thank you very much. Your presentation was very helpful and very informative as well as interesting. And I hope everyone can gain very helpful insights from your presentation today.
Yeah, thank you. Thank you. Have a good day. Yes.
Yes, have a good day, Mr. Keith. And for everyone, please don't forget to fill in the attendance link in order for you to get your e-certificate for today's event. This is Shafira, the master of ceremony for today's event, and I will say thank you to everyone who have participated and have a good day, everyone. See you in our
Yeah,
next
see you.
events.
Bye-bye. Yeah, bye-bye.
Thank
Yeah,
you,
bye-bye.
Mr. Keith.
Bye-bye.